Let's start. After reading topic name, you all might be thinking that it's quite difficult, but it's very interesting, believe me. Do you remember this equation? This is called Pythagoras theorem. Now see Fermat's last theorem. Pythagoras and Fermat's last theorem are quite relatable. The only difference is Fermat is valid for powers greater than 2. But I have not told you who is Fermat. Fermat is a French mathematician born on August 17, 1601. One day, as a hobby, he was studying a book, Diophantus of Alexandria, and he wrote, "I have a truly marvelous proof which this margin is too small to contain." So he has not proved last theorem. As we know that Pythagoras theorem gives answer in whole number for any two numbers. Fermat thought that if we change Pythagoras theorem powers into cubic powers, fourth powers, fifth powers, and up to so on n power, does it hold? Then he concluded that it holds for only numbers less than 3, that is, n must be less than 3 only.
For example, first just take two numbers, let's say 4 and 3. Now add the squares of both numbers. Observe that by adding both sides we get a number that is itself a square. For example, 20. Taking under root of 25 we get a whole number. Now take two numbers 5 and 6. Now add cubes of two numbers. Observe that by adding cubes we get a number that is not a cube of any whole number.
As Fermat claimed that he had a marvelous proof of this theorem, so countless professionals and amateur mathematicians have tried to find a valid proof and wondered if Fermat really ever had one. For more than 3.5 centuries, the Fermat's last theorem had been a curious and impossible riddle on the edge of mathematics. But the English mathematician Andrew Wiles, who had been interested in the theorem since the age of 10, proved the Fermat's last theorem by proving the modularity conjecture for elliptical curves and was awarded the Abel Prize, that is Max Nobel, for his work. A German mathematician, Gerhard Frey, had the idea that if somebody could prove the Shimura-Taniyama-Weyl conjecture, then the Fermat's last theorem would automatically follow.
The assumption provided by Gerhard Frey clicked the mind of Andrew, and he started working on the conjecture. To prove the last theorem of Fermat, he must had to prove the conjecture of Taniyama-Shimura. So first we had to learn what are the elliptical curves and the modular forms. Elliptical curves we are talking about here are in the form of whole numbers and fractions, whereas we are talking about the modular forms. So let's get started with the modular forms. What are modular forms? Modular forms are actually really complicated equations. So to make it easier for you guys, just imagine there's a brown paper, and we had converted this brown paper into pieces. We had cut this brown paper into pieces of same size, like this. Now if we draw the modular form into this paper, we can see each slice have the same symmetry. Now if we talk about a circle, we can see there is no symmetry in each pattern. They are different. First slice is different from the last one. और ये बात प्रूव करने के लिए कि मॉड्यूलर फॉर्म एक पार्ट है एलिप्टिकल कर्व का, वाइल्स ने इसको डिफरेंट वे से देखा. इसने इसको डायमेंशन की फॉर्म से देखा कि अगर हम नीचे से ऊपर जाएं और ये एक 3 डायमेंशनल स्पेस हो तो हमें एक कॉइल मिलेगी, लाइक दिस goes on and we will get a coil of infinite number of rounds. So अगर हम इस कॉइल को लंबा करके खींच दें तो हमें एक ट्रांजिशनल सिमेट्री भी मिल रही है. लाइक एक कॉइल भी या एक सर्कल का 3 डायमेंशनल फॉर्म भी 2 डायमेंशनल से बनी हुई है, मीन्स के मॉड्यूलर फॉर्म्स जो कि बिल्कुल ही कर्वी स्पेसेस हैं वो एक दूसरी डायमेंशन के अंदर एग्जिस्ट करते हैं जो कि है एलिप्टिकल कर्व्स। And this is how Wiles proves the Fermat theorem using Taniyama conjecture.
जैसा कि हमने अभी कर्व में डिस्कस किया कि एक्स क्यूब प्लस वाई क्यूब इज़ नॉट इक्वल्स टू जी क्यूब, सो इट इज़ टोटली इम्पॉसिबल कि हम दो क्यूब्स के सम को एक क्यूब लिख सकें। अब हम फर्मा का एक स्पेशल केस डिस्कस करेंगे, डेट इज़ n इज इक्वल्स टू 4। सो n इज इक्वल्स टू 4 की इक्वेशन को हम कॉन्ट्रडिक्शन मेथड से प्रूव करेंगे और हम ये एग्जम्पशन लेंगे कि अगर x की पावर 4 प्लस y की पावर 4 इज इक्वल्स टू z की पावर 4 का सोल्यूशन है, सो x4 प्लस y4 इज इक्वल्स टू z स्क्वायर का भी सोल्यूशन हमारे पास एग्जिस्ट करेगा। GCD x प्राइम y प्राइम इज इक्वल्स टू 1, सो हम अपनी इक्वेशन को इस फॉर्म में भी एक्सप्रेस कर सकते हैं कि x प्राइम स्क्वायर का स्क्वायर प्लस y प्राइम स्क्वायर का स्क्वायर इज इक्वल्स टू z प्राइम स्क्वायर। जैसा कि हमारे पास ये तीनों वैल्यूज़ पैथागोरियन ट्रिपल की रिक्वायरमेंट्स को पूरा करती हैं, तो इनमें से किसी एक को इवन और दूसरे को ऑड होना चाहिए। नाउ टेकिंग x प्राइम एज इवन, देन देयर एग्जिस्ट अ रिलेटिव प्राइम इंटीजर, सो x विल बी ग्रेटर देन t एंड विल बी ग्रेटर देन 0। नाउ x एंड y एंड z को हम लोग पैथागोरियन ट्रिपल की वजह से इन इक्वेशंस में लिख सकते हैं। अब अगर हम एजम्पशन ले लें कि s हमारा इवन है, तो मॉड फॉर्म में इसका आंसर 1 आना चाहिए, जबकि हम इसका जब सोल्यूशन करते हैं, इसमें वैल्यूज पुट करते हैं, वी गॉट 3 मॉड 4 विच इज़ इम्पॉसिबल। सो हम कंक्लूड कर सकते हैं कि हमारा s इवन नहीं है, सो s विल बी ऑड। अब अगर हम s को ऑड लेते हैं, देन वी ऑब्जर्व दैट t विल बी इवन। So by putting the values, we get x prime square by 2 square is equals to 2r. So x will be even, y and z will be. Product of any two relative prime integer is a square only if each integer itself is a square. So हम लोग कह सकते हैं कि t square plus y square जो है वो s square के इक्वल है। क्योंकि GCD ST का 1 है, तो इट फॉलोज डैट कि GCD XY भी 1 होगा। सो T, Y प्राइम और S को पैथागोरियन ट्रिपल की वजह से हम इन इक्वेशंस में लिख सकते हैं। अब अगर U और V हमारे दोनों स्क्वायर्स हैं, सो हम U को लिख सकते हैं x1 स्क्वायर और V को हम लिख सकते हैं y1 स्क्वायर, और इस इक्वेशन को हम इस फॉर्म में भी रीराइट कर सकते हैं। Z1 और T पॉजिटिव होने की वजह से हमारे पास इसके साथ एक इनइक्वालिटी भी आ जाती है, डेट इज़ Z1 स्क्वायर इज़ ग्रेटर देन 0, और जिससे हम ये कह सकते हैं कि Z1 इज़ ग्रेटर देन Z2 इज़ ग्रेटर देन Z3। देयर इज़ फाइनाइट सप्लाई ऑफ पॉजिटिव इंटीजर, सो इट इज़ अ कॉन्ट्रडिक्शन, so it is impossible to solve this theorem. Now Fermat theorem allows mathematicians to formulate new techniques and the formulas. But one of the most important application of Fermat theorem is in the field of modern cryptography.
Probability theory, calculus, and analytical geometry are the contribution of Fermat in the world of math. He also worked in pure mathematics like Fermat-Little theorem. Mathematicians are still searching for its application, and we hope so. It does not contain as long time to understand this theorem as Pythagoras theorem contained. We really hope that the questions that are still unanswerable and rise in our mind about the Fermat-Last theorem will get its answer in future. We are really proud that we have enough mathematical formula, that being a mathematician, we hope that we can perform any hard task in the field of mathematics in future using the techniques and tools of mathematics. Thank you.
Someone had resolved this problem 300 years ago, but no one had ever seen the proof. No one knew if there was a proof. and people ever since had looked for the proof. And here was a problem that I, a 10-year-old, could understand.
So the first night I went back and stepped on it. I checked through it again the next morning, and about 11 o'clock I was satisfied, and I went down, told my wife, I've got it, I think I've got it, found it. And it was so unexpected. I think she thought I was talking about a children's toy or something. I said, got what? And I said, I fixed my proof, I've got it.